Swayam Prabha. Digital India. Educated India.
So, let me redraw the circuit I had. We define V1, V2 and V3 with respect to the reference node, which is this. Okay. So, now I have to write I11 plus I12 equals I1. Okay. I11 plus I12 equals I1, and these are currents flowing out of node 1. This is node 1, this is node 2, this is node 3, and this is the independent current pushed into node 1. Okay. Now, what is I11? I11 is nothing but V1 divided by R11. Okay. So, I11 is V1 divided by R11, which is V1 times G11. Okay. So, I have to write V1 times G11, and I12 is nothing but the voltage across this resistor. Okay. If I call the voltage across this resistor as V12, it will be V12 by R12. But I have chosen the node voltages V1, V2, V3 with respect to the reference node as my primary variables, and I will write everything in terms of those variables. So, V12, that is the voltage across this, is nothing but V1 with respect to the reference node minus V2 with respect to the reference node. This is apparent from Kirchhoff's voltage law. Okay. So, this is V1 minus V2 by R12, which is V1 minus V2 times G12. Okay. So, I have V1 times G11 plus V1 minus V2 times G12, and the whole thing equals the independent current source flowing into node 1, and that is basically I1. Okay. So, that is my equation for node 1. This is KCL at node 1. So, the equation represents Kirchhoff's current law, and the individual terms in the equations have been written using the element relationships, in this case of a resistor. Okay. When I write the current here to be V1 times G11, I have used the element relationship already, and similarly, when I write the voltage across R12 to be V1 minus V2, I have used KVL, and V1 minus V2 times G12 is the current flowing in R12. I know this because of the VI relationship of the resistor. Okay. So, this is how I set down the equations, right. Now, let us go ahead with the other two nodes. So, let me do it for node 2. So, again my convention is to always take the current flowing away from node 2. Okay. So, I have to take the sum of the current in R12, R22 and R33 in this direction flowing away from the node to be 0, because there is no independent current source connected to this node. Okay. We have only resistors. So, what is the current through R12 in this direction flowing from right to left? It will be V2 minus V1 divided by R12. Okay. V2 minus V1 divided by R12, which of course is V2 minus V1 times G12. Okay. For nodal analysis, it is lot more convenient to use conductances instead of resistances while writing down the equations. That is what I am going to use. And by definition, G12 is 1 by R12, G11 is 1 by R11 and so on. Okay. The current through R22 is nothing but V2 times G22, because V2 appears across R22. And finally, the current through R23 is V2 minus V3 times G23. Okay. So, again we are looking at currents flowing away from node 2. Please be mindful of the direction of currents. It is always currents flowing away from a particular node equals the independent current source being injected into that node. The independent current source being injected into node 2 is 0. So, the sum of all of this is just 0. And finally, for node 3, we have to sum these two currents, current flowing into R23, current flowing into R33, sum of those two equals I2. The current flowing into R23 in this direction will be V3 minus V2 times G23. The current flowing in R33 is simply V3 times G33, and it equals the independent current flowing into node 3, which is I3. Okay. Now, I will rearrange these into a nicer form. What I will do is, I will collect terms containing a particular voltage. Okay. That is V1, I collect all of the terms containing V1. In this case, I have V1 times G11 here and V1 times G12 over there. So, I will write V1 times G11 plus G12, and I will take the terms containing V2. In this case, there is only one of them. So, I have minus V2 times G12, and I do not have any terms involving V3 at all. Okay. These currents V1 times G11 plus G12 minus V2 times G12 equals the current I1. Okay. And similarly, I collect terms containing V1. I have only one of it in the second equation, minus V1 times G12, and terms containing V2, there are 3, V2 times G12, V2 times G22 and V2 times G23. Okay. And finally, terms containing V3, and there is only one of them. I have minus V3 times G23, this whole thing equals 0. And finally, for the last one, I will do the same. There are no terms with V1, minus V2 times G23 plus V3 times G23 plus G33, this equals I3. Okay. I have 3 equations and I have 3 variables to solve for, V1, V2 and V3, and from that I can easily figure out what happens in the rest of the circuit. Okay. So, this set of 3 equations, and for an n node circuit, n minus 1 equations, these are known as nodal analysis equations. Okay. So, for this particular circuit, I1, R11, R12, R22, R23, R33. Okay. And I have got my equations which are in terms of these node voltages V1, V2, V3 with respect to the reference node. Okay. So, what did I have? At node 1, I had V1 times G11 plus G12 minus V2 times G12 equals I1. At node 2, I had minus V1 G12 plus V2 times G12 plus G22 plus G23 minus V3 times G23 equals 0, and finally, at node 3 I had minus V2 times G23 plus V3 times G23 plus G33 equals I3. Okay. And this is usually written down in a matrix form for convenience, and the matrix has a nice structure which once you identify you will be able to put down right away, okay, without going term by term as I did in this particular example. So, what I do is I write this set of linear equations. This can be done for any set of linear equations as a matrix G11 plus G12 minus G12 0 minus G12 G12 plus G22 plus G23 minus G23 and finally minus G23 G23 plus G33. Okay. This is a matrix times the vector of variables V1, V2, V3, and this will be equal to the vector of independent sources I1, 0 and I3. Okay. There is nothing new in this. All I have done is to written down these equations, this set of 3 equations in 3 variables in matrix form. So, I have a 3 by 3 matrix times a variable vector equals the independent source vector. Okay. Clearly, the first row corresponds to the first equation G11 plus G12 times V1, which is what we have here, minus G12 times V2, which is what we have here, equals I1, which is what we have over there. So, I can go term by term and identify each equation. Okay. So, the first row corresponds to node 1, the second row to node 2 and the third one to node 3. Okay. So, the nodal analysis equations, which basically are written down as currents flowing out of a particular node in resistances equals the independent current source being injected into that node, that I have put down in a matrix form. Okay. So, these are the nodal analysis equations, and I have a 3 by 3 conductance matrix. Now, in general, in an n node circuit, it will be n minus 1 times n minus 1 conductance matrix. I will denote that like this. I will put the square brackets to just show that it is a matrix. Okay. And what is this? This is the vector of variables, and the size of this in this case is 3, that is 3 times 1 matrix, or in general it will be n minus 1 times 1. So, basically the vector consists of all the node voltages with respect to the reference node, and there will be n minus 1 of them. Okay. And finally, the entry on the right hand side, this corresponds to the vector of sources. Okay. This corresponds to a vector of sources. So, what I have is conductance matrix G times the vector of voltages V being equal to the vector of independent sources I. Okay. So, this is this and this is that. Okay. So, this gives us a compact notation. Okay. So, this is like Ax equals y, and to solve for x, you do x equals y divided by a, when a is just a number, when it is a scalar. Okay. But exactly the same thing will apply here as well. So, to solve for the vector v, you do G inverse times I. Okay. So, this is the solution to the nodal analysis equations. Okay. So, you first set up the nodal analysis equations. I will point out the structure of the conductance matrix. Once you understand it well, you do not need to first write down the equations and then put it in a matrix form. You can put it in a matrix form right away. The matrix equation can be solved for small matrices, usually 2 by 2 or 3 by 3. You can do it by hand. Otherwise, you resort to a computer. Okay. So, there will be a systematic way of putting down the conductance matrix, and therefore, a systematic way of solving for a large circuit. Okay.